In this video, we'll learn all about Prolog unification. So in the process of trying to satisfy a query, Prolog is going to try and match some terms that are in that query to terms inside the knowledge base. So this matching of terms, in order to determine whether or not they do match, Prolog will follow what's known as the unification algorithm. Unification is a lot like asking, can these terms be made to be equal? So for example, let's open up a Prolog window here. If I say 1 equals 1, as a query, that's not a statement, it's a question saying, does 1 equal 1? Or can I say that these two terms are the same? And that's obviously true because 1 is just 1. Similarly though, I can say something like 1 equals x. And this isn't saying assign the value of x to 1 as we'd normally read the equals operator. This is actually saying, can these two terms be unified? And that's true if we give x the value of 1. So if we make that assignment, then they will unify. Okay, so unification is the process of determining if these two terms can be somehow matched. And there's a bunch of rules for that. So the unification rules are as follows. So first off, any numbers, any atoms, or all these constants, they'll unify with themselves. So kind of like in Scheme, how these things were all self-evaluating, they have their own value. In Prolog, they'll unify with themselves because, again, they're just simple constants. Now, if we have variables, any uninstantiated or unbound variables, they'll be matched or they can unify with anything. Okay, so unbound variables will unify with other unbound variables. So if I say, can x equal y? That's true. If they're both unbound, then sure, why not? They can have the same value. They don't even need to have a value, but they can unify. Now, unbound variables with constants or any other term will also unify. So if we have, for example, x equals 5, that's true if x was unbound. We can assign it the value 5, and then they now are the same thing. So we can make them the same. Now, with compound terms, it's a little bit more complicated. First off, it's true if they have the same name and arity. So we'll see compound terms down here. It's true if they have the same name and arity, the number of components in their terms, and if each one of those arguments or those inner terms can also subsequently unify. So if they have the same functor, the same number of arguments, and all those arguments can individually unify, then we can say two compound terms will unify as well. So for examples, if we have John and John, those are just atoms, so those obviously will unify because they're the same term, they're the same constant. Now if we have John and Mary, those are two different constants, so there's no way to make those the same because they're distinct. Same thing with numbers. 1,234 will unify with 1, 2, 3, 4 because, again, they're the same constant. But if we throw a decimal in there, we make two different constants here, those won't unify because you can't change what a constant is. Hence the term constant. Now, if we have compound terms like owns John book, that will unify with an identical compound term, but the process that it follows says, does it have the same functor, so the same name, yes. Does it have the same arity, so we have 2 and 2, so yes. And then element per element, do they unify? So will John unify with John, and will book unify with book? In this case, both of those will, so then we can say the entire compound term will unify. Now, if we have variables in the mix, same sort of thing applies, so the two names match, so that's great. The same arity, so 2 and 2 again, so that's good. And then we go through recursively saying, can the inner terms unify? So we have x and John, and that follows into rule 3 here, where we have an unbound variable and a constant. So that's true, or that will unify if x gets the value John. So now we have x is John, and then we have to find out, will book unify with y? And that again follows to rule 3 here. We have an unbound variable y and a constant atom book. And that'll again unify if y gets the value book. So we can say these two compound terms, owns x book and owns John y, can unify if x gets the value John and y gets the value book. And these rules can go entirely recursively, so if we look at these two compound terms and ask, will these unify? Well, we have the same name, so A, the same number of terms, so 1, 2, 3, and then this one has 1, 2, 3 as well, so both have arity 3, so same name, same number of terms, and then we recursively say, can the inner terms unify? So we have the atom B and the variable B, those will unify. We have the atom C and C, those will unify as being the same constant. And then we have, recursively, we have another compound term. I'll leave you to walk through all the individual steps, but essentially these will unify if all the variables bind to all the different constants that are in there. So just recursively applying these rules over and over again to determine will these two things unify. Now, when we ask Prolog to unify two things, so for example, when we make a query and it wants to match that query to something in the knowledge base, it has to try and unify that. Or if we just straight up ask it, does this equal that? In that case, it tries to unify those two terms. In order to do so, it will follow the unification algorithm. And the unification algorithm here is essentially just a repeated application of the unification rules that we just learned. So the result of this unification algorithm, so the input, let's start there actually, is two terms we want to know, can they unify? So we have a query and something in our knowledge base, or again, something we typed in, x equals y, or x equals 5, whatever we typed into the query space. So the input, is two terms we want to know, will they unify? And the output will be the most general unifier of T1 and T2. So a unifier is something along the lines of this, where we want to know, will these two things unify? And that's true if X is bound to John and Y is bound to book. So the unifier is those bindings, the set of assignments or associations that need to be made in order for that unification to be true. So if they are true, great. We'll see how that comes to pass. But if they are able to unify, then this algorithm will return not just that they can unify, but also the most general unifier of those two things. Now, most general just means if we have unbound variables, they can bind to other unbound variables. We don't have to give them values in order for some of these unifications to happen. So we'll make the fewest assignments possible as we're doing this. Now again, notice this algorithm doesn't say anything about where we find the terms T1 and T2 to be unified. This unification algorithm just says, given two terms that we've somehow asked Prolog to determine can they unify, this is how Prolog makes that decision. So let's walk through this a little bit. So again, the input is two things to unify. The output is the most general unifier. The initialization of the state is that the unifier starts off as empty, and we have a stack that contains all of the unifications that we want to, because there's going to be a recursive process here. So initially the stack just has the top level goal. Does T1 equal T2, or can it unify with T2? And then we also have a failure flag here that will break out if anything goes wrong. Now, so long as there's something on our stack, and we haven't failed yet, then what we'll do is we'll take the first thing off the stack. So we put T1, T2 as the first thing. Now we're just going to pop them off. So let's argue we want to say, does John equal John? So T1 and T2 are both the atom John, and now we pop those off. So X is John, Y is John. We want to know, can these two things unify? So this while loop essentially just goes through the rules here and just says, under all these different cases, these will successfully unify. Anything else that doesn't match one of these cases, set failure to true, and that'll break out of the loop and return false eventually. So if we're asking, does John unify with John, X isn't a variable, Y isn't a variable, because they're both atoms. So then we come down to this one. X and Y are identical constants. In that case, that would be the case. And if that is the case, it just says continue, so it goes back up. The stack is now empty because we popped the only thing off, so that's done, and we'll just output Q. So it's real easy if they're two atoms, just, they look the same, so they're done. Now if we have a variable in there, so let's say something along the lines of, let's just use x equals 1, something like this one here, x equals 5. So to determine if that will unify, again, we put it onto the stack. It's the only thing we pop off the stack. And x is a variable and y is not, because y is the value 5. So two things happen. I'll talk about this in just a second. But the second thing is that we add x equals 5 to q. So that's our result. Okay, so we said these will unify, and a variable will unify with a constant, under the condition that we now remember that as the unifier. We use that binding that x now has the value 5, and we store that in our output. Now this other line that I skipped over here is if we have other things in our stack, or in the unifier already, then those bindings or those variables also need to be changed. So we said x equals 5. So substitute 5 for x everywhere in the stack and everywhere in our result. So if we just had the variable x in the result already, or in any other unifications coming up on the stack, then we're going to make that substitution that x gets the value 5 all throughout. And this is how scope gets controlled in Prolog. We'll come back to that when we actually have stuff on the stack. So if x equals 5, that's great. We set that unifier into our output, and because we popped the only thing off the stack to do this step, when we come back up, the stack is empty, and we will return Q, our output. So it says true if x equals 5. Again, not terribly enlightening because x equals 5 is a pretty easy unification to make. But let's do a more involved one. Let's do something like owns x book and owns John Y. So T1 is owns x book, T2 is owns John Y. So we put those onto the stack, and then we immediately pop off that top level combination, where x now equals owns x book and y is owns John Y. Now, x is not a variable because it's a compound term. Y is not a variable for the same reason. They're not identical constants, neither are they variables. So we come down to this bottom case here, where x is a compound term with some functor f and some list of arguments. And y is a compound term with the same functor f and the same number of arguments. Right? So this goes from 1 to n, that goes from 1 to n as well. Okay. So implicit in this is that the x and y, in order for them to unify, need to have the same functor, the same name here, and they need to have the same arity. Now if they do, then what we'll do is, for each one of these subterms, so x1, x2, x3 all the way to xn, and for y1, y2 all the way to yn, we'll take each pair and push those onto the stack. So for our case here, we said owns matches owns, so f in this case is owns, and arity is 2, so that's great. And then we'll say for each pair, so we got x equals John and book equals y. So we say, can John unify with x, and can y unify with book? And that's what goes onto the stack. So now there's two things on our stack for those two sub-elements. So we come back up to the top. The stack is not empty because we pushed new things onto it. So we pop the top one off the stack, and that's can x unify with John? We've kind of seen how that works already with our x equals 5 example. X is a variable, y is not. So we'll add x equals John into our result, and we'll substitute John for x anywhere else in the stack and in the output already. Now in this case, this variable only shows up once, but if we had a second instance of this variable in here, it would also be on the stack. If we had, for example, owns x book x and owns John y z. So then x at the end here would have to unify with z at the end. And that would only work now, because we've given the value John to x, that would only work if z also gets the value John. Now that's a bit hypothetical, so let's stick to the example that we have here. So owns x book, owns John y. So we want to know, does x unify with book? It does if we set x to the value, does x unify with John? It does if we set x to the value John, and we substitute John for x anywhere else that it appears. In this case, nowhere, but if it did appear, we'd make that substitution. All right, and that's the end of that one. So we come back up, we pop the next thing off the stack, which is book and y. So x equals book and y equals y, conveniently. So that falls into the second case, which is pretty much the same as the first case, just in reverse order here. Y is the variable and x is not. So we make that substitution, we add that unifier into our output. So in this case, y equals book. And if y appeared anywhere else in our stack, so in the upcoming more combinations we had to make, or in our output that we've already created, then we make that substitution as well. So it repeats and goes through. I invite you to work your way through the algorithm using these, or come up with your own combinations, perhaps one that has multiple repetitions, and you'll see that this algorithm walks through all the things that you need to know. But more important than understanding the step-by-step process of the unification algorithm is understanding the implications of what it requires, or just getting a sense of when two things will unify. So I feel understanding these rules should take you through most of that. And to that end, let's do some more examples. Now, normally, this would be in a lecture room filled with people, or half filled with people at least, and I'd be demonstrating these and asking you guys to explain whether or not they would or wouldn't unify, and if they would unify, what the unifier would be, if they wouldn't unify, where the failure would occur. But since I'm sitting in my office alone talking to people who won't hear this for probably several more days, I'm just going to go through and walk through these examples on my own and sort of present those unifiers to you as we go. So let's get Prolog back up on the screen here. Now, as I mentioned before, unification happens in two main situations, a few other spots, but the two main situations is, one, if we're putting in a query against a knowledge base. So if I said something like mortal Socrates here, that would be true if this term that I typed into the query could unify with something in the knowledge base, following the rules that we just saw. Now, I don't have a knowledge base loaded in here, so the unification we're going to do is with the equals operator. So I'm going to type in something like 42 equals 42 and determine, will this unify? So term 1 is on the left, term 2 will be on the right, just on either side of the equals sign here. Now, obviously this one's true because they're the same constant, so we get true there. Similarly, or not quite so similarly, but similarly easy, if I said person x equals person Bob. So we have the variable x and the term Bob, both within this relation of person. And this is true if x gets the value Bob, right? So they have the same functor, both arity 1, and then we recursively apply the unification algorithm to the inner terms, so does x unify with Bob? And now we have a variable and a constant, so that will unify, giving the variable that constant. So true if x equals Bob. And if I said person Alice equals person Bob, we could walk through the whole algorithm here, but we can see that's probably going to fail when we try and unify Alice with Bob. So there's same function, same arity, but the inner terms won't unify. So there's no way to make Alice equal to Bob. Okay. We could do another one like owns x car equals owns Bob x. Now, this one might look like it unifies at the surface, right? We have, no, sorry, if I typed it proper. There we go. Owns x car and owns Bob x. On the surface, this looks like it should unify, right? We have two functors that are the same. They're both arity 2, so that should be fine. Then we have a variable with Bob and car with a variable. Now, the issue here, though, is that we've used the same variable for both of these spots. So we have, walking through the algorithm, it'll unify the functor and the arity fine, and then goes through and recursively tries to unify each of the individual terms. So if we say, will x unify with Bob? Sure, why not? X is an unbound variable, and Bob is just a constant, so that will unify, with the result being that x now equals Bob. But as I mentioned before, it's going to unify the value of x, or make that substitution that Bob gets, that x gets the value Bob, all throughout the remaining stack. So on the stack is this does car unify with x query. And now if we replace x with Bob, now we're saying does car unify with Bob? And now those are two separate constants, so it won't unify. Okay, so x will unify with Bob, fine, but then when we go to unify car with x, this x now equals Bob, so we can't. We get false. Now we can fix that obviously by using a different variable like owns x car equals owns Bob y. Now x unifies with Bob and car unifies with y, so there's no real issue there. Okay, on to another one here. How about f of x, y, z equals g of 1, 2, 3. So we have the same terms, and each one of the terms is a variable. So x could get 1, y could get 2, and z could get 3. The issue with this one, though, is that we have the functor f and the functor g. We have two different functors, so it's going to say these two terms can't be unified. So it won't even get to the point of trying to unify the individual parts. So different names won't unify. Similarly, if I say f of x, y, z equals f of 1, 2, we have the same functor. Now we have different arity, so before even trying to unify the individual terms, Prolog will determine these things are different size, so they definitely won't unify. Okay, so that's false. How about f of x, variable y, z is equal to x, y, z. Now on the left here we have a functor f with arity 3. And on the right we have this variable x and then arity 3. Now if I run this, we get, in fact, a syntax error. So it doesn't even get to the point of determining can these two things unify, because we are not allowed to have variables as the functors of compound terms. So recall, compound terms need to start with an atom, that is to say a lowercase symbol, or at least a symbol that starts with a lowercase, and then a list of terms. So in this case, this x here is an invalid syntax, so it just crashes before we get close. All right, let's do some tricky ones now. A bit of recursion in here. So k, s, g y equals kx tk. So again, walking through our algorithm, we can see same functor, so k and k, the same arity, so we have 2 and 2, and then we walk through and try and unify the individual terms. Now we have this compound term, s of g, and a variable, x. Now x will unify with any term, whether it's an atom, a number, or a compound term. So long as that variable is unbound, x will unify with it. So the unbound x bounds to s of g, so now x has that value. And then y, again an unbound variable, will unify with this compound term. So we have these two things can unify if x equals sg and y equals tk. So true on the condition that they get values. So you can see our unifier pops out, and those things can unify under that condition. On to this one. So similarly, we could say ksg of y equals ky of tk. Okay. Now you might notice that these examples are completely meaningless, and that kind of highlights really the focus of how Prolog works. It has no semantic knowledge of anything that we're trying to accomplish here. It just takes the structure of terms and applies the unification algorithm, just walking through pattern matching as it goes to see, can these two things fit together or can they not? So in this case, we'll walk through the same algorithm. So we have same functor k, same arity 2. So we walk through the individual terms. Can s of g unify with y? Sure, why not? So we get y gets the value s of g. But now when we say, will this unify with tk, this variable y is no longer an unbound variable, because the step before, we just unified it with sg. So now we're saying, can sg unify with tk? And those are different, essentially different constants, right? We have different functors, different arguments, so they won't unify. So sg can't be equal to tk, so the whole thing is false. Okay, let's do another one here. K of sg tk is equal to kx of ty. So again, we ask, same functor k, same arity 2, and then we go to the individual terms. So x can unify with s of g. We have an unbound variable x and this compound term sg, so no trouble there. And then we ask, what about this term here? tk and t variable y, can these unify? Well, we're following the same rule. So we have the functor t, great, so functor t on both of them. We have arity 1 in both cases, so one argument. And then we recursively ask, can those arguments unify? And we have k unifies with this variable y. And I see no reason why the unbound variable y can't unify with the constant k. And in that case, again, success. All right, near the bottom of these, there's a few more to go though. Ks of k with x and ks of x with k. So this variable k popping up everywhere doesn't really affect anything that it's getting reused everywhere, because it's just a constant, so it's not going to change value as it gets used in different places. But again, we have the functor k, and we have arity 2. The first argument is s of k, and then we have s of x. So to say if those can or cannot unify, we walk through the algorithm. So the same functor s, same arity 1, and then we have the argument k unifies with the variable x. Sure, x is unbound, so no troubles. So now x has the value k. We come to the next step and we say, can x unify with k? Well, sure enough it can if x has the value k, which it already does. So k equals k, and the whole thing is done. So that's true if x gets the value k. Bit of a trickier one here. I recommend pausing this video between, I probably should have said this at the top of this. It might be a good idea to pause this video between examples, moving forward at least, and see if you can figure these out before I give you the answers, because it's a good exercise. All right, comma f of y. Does that unify with q, a, g, f of b, comma a, and x? So a slightly more involved example here, but still following the same rules. So same functor, great. Same number of arguments, 1, 2, 3, 1, 2, 3. Yep, seems fine. So we go through and individually unify each one. So will A unify with A? Sure. Two constants that are identical, no problem. Will g of xa unify with g fb of a? Well, let's walk through the algorithm and find out. So same functor, arity 2, no troubles. Then does x unify with f of b? Yeah, x is unbound, so it can unify with anything. And will a unify with a? Yes, because again, same constant. So altogether, g xa will unify with g fba with the unifier that x equals f of b. So now we come to this last step and we say, will f of y unify with f of b? Well, we have the same functor f, the same arity 1. We have the variable y unifying with the argument b. Technically, it's inside this variable x, but we can see it here inside this b. And yeah, that's true if y gets the value b. So altogether, this thing will unify if x equals f of b and y equals b. And again, notice the scope of these variables. So when x was bound here because of unifying with this, it stayed bound. Oh my God! It stayed bound to the entire thing throughout the entire term. So x was bound to f of b later on when we referenced x at a different point. I'm gonna pause this for a quick sec. All right. So continuing on, we have. Next example, 3 more of these. R, C, H of x equal to R, Y, F of A. Now, will these unify? So we can walk through the algorithm again. C unifies with Y, no trouble, with now Y having the value C. And we're asking, will these two terms unify, h of x and f of a? Well, x could unify with a, but we have the functor h and the functor f, so those won't match. The arity's fine, but the functors don't match, so the whole thing fails. So false. Okay. We have px, x comma f of y equals pa f of g of z. So will these unify? Well, x will unify with a, p matches p, arity 2. Then going into the terms, x unifies with a, so long as x gets the value a. And then we say, can f of y unify with f of g of z? Now, that's true under a number of conditions, right? We could say that that's true if y gets the value g of z and z gets the value 1. It's true if y gets the value g of z and z gets the value 2. If z gets value 3 or 4 or 5. We could assign a value to z, but we don't have to, right? There's neither side of this ever reuses the variable y or the variable z in order to determine if that will match something else further down the line. So there's no reason to apply a value to z in this instance. So we could say this is true if y matches all of this, including the unbound variable z. So we'll say x gets the value a and y gets the value g of z. This is why it's known as the most general unifier, because by not assigning a value into this unbound variable, the binding, or this unification, remains as general as possible. So we could then use this in, let's say, the next term, as these variables would continue on throughout the rest of this clause. So maybe somewhere else further down the line, we would need to have a value associated with those two things. By creating the most general unifier, as to say, again, not binding a value to z unnecessarily, then we're leaving that door open to be bound later on, or to match more things further on down the line. Okay. I think that covers pretty much all we need to see for this. So let's do one big practice example then with all of the material that we've just covered here. So you can find all the code that I create in these lectures up online. Stuff that I'm doing inside, just the queries that I write down, I won't, but obviously you can just rewind the video. But I have with me a function here, or sorry, a knowledge base here that I can open up in Notepad. There it is. And set the language to Prolog. Oof, that's going to be a problem. All right, let's just put it back to Perl for now. I'll fix the language on this machine later on. Yeah, just what we have here, this is just a comment describing the structure of our knowledge base. And then we have, what's that, 8 different records representing employees in some fictional business. So the employees are described by an ID, first name and last name, an address, a salary amount, and a date of birth. Now for name, address, date of birth, these are described using compound terms. So name has a last and a first name, address has a number, a street, and a city, and date of birth has a day, month, and a year. So it's all structured quite nicely. And then down at the bottom here, we have a number of queries that we want to ask about this knowledge base. I'm going to bring this to the side and open up Prolog with this new knowledge base. So given this information, we want to ask queries that answer these questions. So what are the details of employee 20165? So that's the ID number. So the ID number is here. Now the strategy we're going to use is just asking queries of Prolog and having Prolog provide the unification to things in this knowledge base. So if I say something like employee 20165, and then something like name, address, salary, and date of birth, so variables for everything else, then this will ask, can I unify this query with something in the knowledge base? Now the only thing that's a constant in this query is the ID. So it's only going to match one of these employees because the ID is unique. Everything else are variables, so these will unify with anything that's put in here. So it doesn't matter what the person's name, address, salary, date of birth are, we're going to unify those with these variables. So you can think of these almost as return variables. We're querying some input information, and by leaving unbound variables for the rest, we're asking those to be outbound information from this query. So enter, and we get all the information about employee 20165. You know, their name is Anna Ray, their address is this address, salary, date of birth right there. So copy this into our comments here, and there's that one. Now the next question is Anna Ray an employee? And we just saw that from the previous, but if we wanted to write a query that asked that, we could ask a similarly structured query. So employee, so that it matches one of these structures, right? They're all employee structures. And from that, we can then fill in the rest of the information with stuff that we know. So we don't know their ID. We don't really care about their ID, right? The question is just true or false, is Anna Ray an employee? So we can use the don't care variable if we don't have that information. Now for the name has to match this given structure. So it has to be a relation of 2 arguments, specifically last name and first name, and the relation name has to be the word name. So you have to say name, bracket. Now we want to know, is Anna Ray there? So last name Ray, first name Anna. And then everything else, again, we don't care. If we want to, for example, get their address, we could put a variable there, but the question just says, do they exist? So don't care about the address, don't care about the salary, don't care when they were born. Okay, so just fill in the information that we do care about, and it will return true in this case. All right. Next we have retrieve just the first name of employee 20163. So a similar query to this first one where we had just the ID as our input, but now the output, we only really want the first name. Now, the output last time gave us this structure, and we don't want to grab that whole structure, so what we're going to do is provide that structure in our query so that it matches with the structure in the knowledge base, and what comes out then will be just the name, 20163 John. Okay, so retrieve just the first name. So again, we're going to say employee, provide the structure of the outside relation here. And that has a bunch of spaces. We have the ID, sorry, 20163 is the ID. For the name, we don't care what their last name is, but we do care about their first name, so we'll say first name as a variable. Okay, and again, we don't care about the address, salary, or date of birth, so we can leave those all blanks. So we have information that we have, so we can provide those as constants, and information that we want, so we can provide that as a variable. Now, in this case, we don't want this structure around that in our answer, so we'll provide that in our question. That will then unify. So to walk through the unification algorithm for this one, because it's a bit interesting, we're asking, can this entire term unify with something in the knowledge base? So employee matches all of these things, so it'll start at the top one and say, okay, 20163. Will that unify with 20163? Two constants that are the same, so no problem. Next it says, can this term unify with the second term? So we have the functor name, that's great. Arity 2, that matches. So then the individual variables. Now we have an unbound variable here, the don't care variable. That will unify with Smith, but we don't care about it, so it won't store that value. So the underscore here says essentially, don't put that result in the output of the unification algorithm. It's a placeholder so that it works, but don't store it. Then the second one here, first name, we have an actual variable there, so that will unify with this atom, where first name now equals John, and that does get stored in the result. Everything else is a don't care variable, so it'll match underscore unbound variable matches with this term, underscore unbound variable matches with this term, and the underscore unbound variable matches with this term. Now, notice with the underscore, in addition to not adding it to our output, it also doesn't create that substitution throughout the rest of the stack. So when underscore here unified with Smith, it didn't make all of these underscores equal to Smith. Each underscore you can think of as its own separate variable. So this is underscore 1, this is underscore 2, underscore 3, underscore 4. You can never re-refer to an underscore, the value that's in an underscore variable, because the underscore don't care. Okay. So with all that, we can run this, and we should get the answer. First name is John. Now notice it's hanging here, waiting for me to tell it should I keep looking or not. And that's because there are a bunch of other employees that it hasn't yet looked at. So it looked at this one, and that one worked, but maybe all of these other employees might work as well. Now as humans, we can quickly glance down and see that the ID 20163 is unique, so it shouldn't work. So if I backtrack here and say, yeah, give me another answer, comes up false. Okay, so first name John, that was the correct answer the first time, and that says, if I didn't want that, is there anything else? No, there's nothing else. All right, so let's take this and put it in our solution. Okay, and then on to what is the salary of John Smith? So this follows a similar pattern again. Once you get the hang of it, it makes some consistent sense. So we don't know the person's ID, and we don't care about the person's ID, so underscore. We do know the person's name, so we're going to say name. We know it's John Smith, so that's Smith, comma, John. Now the structure is ID, name, address, salary, date of birth. We don't care about their address, so that's an underscore. We just want their salary, so we'll put in salary as a variable. And we don't care about date of birth, so underscore again. So employee with all of these space holders should match one of these employee records. The only one that will be successful, though, will be the one that has name set to the constant Smith John, which is right there, Smith John. And then throughout that unification, determine will employee match this this query. It'll unify salary with 40,000 here, and then we can walk away from that with this new value associated with salary. So the output will be salary equals, and then the salary we're interested in. All right, on to then one other here. I've got a couple more actually. Copy. Who lives in Ottawa? So to answer that question, we have to pay close attention to the structure of our employees again. So address contains a num, a street, and a city. So if we want to know all the people that live in Ottawa, we're going to ask who's one person that lives in Ottawa, and then that'll give us back an answer. If we want additional people, we can just backtrack and get additional answers. So all we really need to do is fill in this block here, this city, as being Ottawa. So let's go with employee. We don't care about their ID. We want to know their name in the end, so we'll just put a name variable here. If we want to have last name, first name, we could also do name, comma, last name, first name, something like that. If we don't want to have this structure in our answer. In this case, it doesn't specify, so it doesn't actually matter. It does ask who, so we should probably give them a name, but it doesn't specify the structure of that result. Right, so name, last name, first name. Next is address. So in address, we have to specify the structure because we're going to supply some information. So an address is num street and then city. Now we don't care about the number or the street, but we do care about the city being Ottawa, lowercase o, so that it's a constant, not a variable. All right, we don't care about their salary, don't care about their date of birth, so those are both underscores, and that's the end of our line. So again, we provide all the information that we have in the matching structure, so it'll actually unify correctly. And any information that we want back as our result, we supply variables. Anything that we don't care about, underscores. And we run that, and we get that's true if the name is John Smith. And if we want to see who else lives in Ottawa, we can backtrack. So semicolon, and that also works if David Palmer is the person we're looking at. And backtrack, Robert Norman is also one of them, and Maggie Smith, and Sarah Tsume, and that's everyone. So we can actually verify by I, so Sarah, Maggie, Robert, David, and John. Great. Okay, so let's take this answer and put it in our results and try the next one. Names of employees born in January. This one's actually really similar to the one we just did, so let's type it out. Employee. We don't care about their ID. We do care about their name. I'll do the short form this time where it just returns the structure. Not employee. Employee. Can't click in here. There we go. So employee, we don't care about their ID. We do care about their name because it says names of employees. We don't care about their address because we just need their date of birth, so we don't need salary either. And then date of birth, which looks like this structure. Date underscore of birth, and then day, month, year. So date of birth, date of birth, day, month, year. So in this case is people born in January, so we don't care about the day. We do care about the month, which will be 1, and we don't care about the year. We run it, and we can see David Palmer was born in January. Where's that? David Palmer's up at the top. David Palmer is born January 12th. And if we backtrack to see if anybody else, Anna Ray was born January 1st. And Anna shares a birthday with Billy Ray, who was also born January 1st. And that's all of them. All right. I think that's that. So let's grab this example and put it in our answers. And we have one last query. Any 2 employees that live on the same street. So this is a bit more of an involved query because now we're not just trying to find 1 employee, but 2. So we can say employee. Let's just take the name because it's useful to see who they are. We need address. That's this one. Address. So we want to know 2 people that live on the same street. So address is num, street, and then city. So we don't care about the num. We do care about the street, but we don't know what that street is. So we'll just put in a variable here. We don't care about the city. Although I suppose technically you could have the same street in different cities, so maybe we should. It doesn't really specify. Keep it simple. We'll just consider the street for this case. We'll assume all streets are unique, which is unlikely. Okay. So employee, we don't care about the ID. We do want the name in the end just to see who they are. We need the street address, and then nothing else about this employee matters. We don't care about their salary or their date of birth. Okay, now if we just run this, this doesn't tell us the names of 2 employees that live on the same street. This just tells us 1 employee and the street that they live on. And this will be John Smith is true. It's true of David Palmer. It's true of Anna Ray. It's true of Billy Ray. It's true of Edward Black and Robert Norman. It's true of everybody, right? The reason being we didn't specify any constants in our query. There's nothing in here that would limit the results. So to put some conditions on that, we'll add a second term to our query. So we have the first term here is grab some employee, get their name, and get the street. The next thing we should do is ask for a second employee that lives on that same street. So by the time we get to the point where the cursor is right now, it will have unified with, let's say, the first one here. Name is Smith John, and street is King Street. So these 2 variables will have values after it's done the unification for this term. So we'll be at this cursor, and we'll have values. Name is John Smith, and street is King Street. So if we ask for another employee, we don't care about their ID. We'll get their name. We'll call it name2, just to use a different variable name. and address underscore street, because we want it to be on the same street. Address, salary, date of birth. Okay. Now, name and name2 can bind to two different things because they're different variables, but street and street are the same variable. So once this version of street has bound to King Street with our first example, it'll go looking for another employee that has a name, any name will do, and has street equal to King Street, because this variable now has that value. And let's see what that does. If we run this, that's true if both the people are John Smith, so John Smith and John Smith, because then he lives on King Street. But we can backtrack and ask, is there somebody else? Well, it's also true of David Palmer, because he lives on the same street as himself. But David Palmer and Maggie Smith both live on Queen Street here. So if name is David Palmer and name 2 is Maggie Smith, then this works. So this one is more what the query is asking, two different employees that live on the same street. But notice Prolog said, I don't care if the name equals name 2 or if it doesn't. Here's one person that lives on the same street as themselves. It's not really the same answer that we're looking for. So what we should do is modify our query a little bit. So up to bring it back. So we've queried out one employee here. So we have the name and the street, King Street and let's say John Smith. And then we go looking for a second employee. Now, once we have that, it will tell us a second employee that has a name and lives on the same street as the first one, but that might be the same person. So what we should do is add in one more condition that says name does not equal name 2. Let's bring this full screen so we can see it all. There it goes. So this block here grabs one employee. This one here grabs a second employee that lives on that same street, possibly the same person. And this one here says, if name 1 equals name 2, then that's false. So it'll backtrack and it'll try something else. We'll talk about how it resolves all this in the next lecture. But what this says is find two employees where the names are different, but the streets are the same. There you go. So that's true for, I'm going to bring this to the side again. That's true for David and Maggie, as we saw before. And if we backtrack, it's also true for Anna and Billy Ray, because I think they live in the same house. And the reverse is also true. In that case, this is still meeting the requirements. It's just sort of matching the other order. So this one says if name 1 is Anna and name 2 is Billy, then this works. But it's also true if name 1 is Billy and name 2 is Anna, right? If it just flips the order. And that's fine. There's not really any way around that other than keeping track of all the previous answers in a list, which is overkill for these types of problems. All right, and we can backtrack. And it's also true if we reverse Maggie Smith and David Palmer. And then there's no other combinations of two people that live on the same street. Okay. Now another way of answering this same question, I'm just going to show you this as well. I'm just going to bring this full screen so it all fits. Instead of having one street variable, we could have done street 1 and street 2. And then here later on said street 1 must be street 2. That does the exact same thing. This is more of a verbose way. You won't see it done as often, but if this is easier for you to understand, if you prefer this version, then feel free to use the longer version as well. And that does the exact same results. There we go. Just mentions an extra variable in the output, but street 1 always equals street 2 because it has to. All right, so let's take this version as our answer. Copy and put that down in our results here. And I think that's everything. So that's the end of this video. I'm going to break up all the lectures into smaller sections, so one topic at a time. So this was unification. Stay tuned for more videos. Next we'll talk about operators and arithmetic in Prolog. So I'll see you later. Actually, I won't see you, but you'll hear me later.